The Virginia SOLs suggest that physics students should be exposed to nanotechnology. And basically, the idea is that when you make things little on the nano scale, which gets you down to the atomic scale, that things do behave differently. If you build things at the atomic scale, you can build interesting and different properties into them. But also, when you work at the atomic scale, you can take advantage of the properties of materials in order to accomplish very unique and interesting things. That if you are working with quantum, of course, that's very different than the way we're used to things behaving. And so there becomes all of this possibility for new materials, cheaper materials, functionality of materials that has never existed before, simply because they are very small. And we are not going to try to get at why that is the case, but I just want to expose you to several possibilities for things behaving differently at the scale of the very small. Computing is the first on the list, and it will be referred to in the video that you're going to see. That originally we got our on and off with mechanical switches, and when we moved to semiconductors, we started taking advantage of the properties of at the atomic level of these materials to make switches that were not mechanical, but were instead because of the properties of the atoms. And this meant that, one, you could build these switches using chemical processes, which is much cheaper, and you can do it in enormous quantities. You could put together circuits photographically. It became very cheap to assemble, very large, because you have many, many switches. You become very powerful. And because it's at the atomic scale, these switches are close to one another, it becomes very fast. And again, to emphasize that when we go from a mechanical thing accomplishing some task to using properties of the material to accomplish the task, you get many advantages that all of which have been sort of suggested here. But that, again, listen for that as you go through the video. The video is going to be a NOVA program from 2013, and I've selected clips from it. But I hope that will reinforce what I am saying now and make several points that have not been made. Two of the materials that, well, graphene, I'm not sure if I pulled the clip on this, but graphene is one of the things that I was introduced to by this NOVA program. It is graphite, 1 atom thick. And so, unlike normal graphite, it becomes very strong. It is transparent, and they will make the point, this you will see in the video, that although it is 1 atom thick, you can see it, which is amazing. But light does pass through. It is transparent, and so you could do things like put your electronics directly on the cornea. That it is a perfect barrier. Forget what this says about water filters here. Very conductive. It's surprising properties that this material has when you make carbon be a sheet that is 1 atom thick. Carbon nanotubes are rather like this sheet of graphite, but it gets wrapped around into a tube, and they have been around longer than the graphene. That they also are surprisingly strong and surprisingly conductive. Not as conductive or strong as graphene, but still. One of the things you will see is taking these carbon nanotubes, very short carbon nanotubes, and making what they call whiskers, nanotube whiskers, and they have amazing properties for causing things to become repulsive to fluids, and so you can make things waterproof, as you will see in the visuals. Another thing we discover when you make things small is the property of their color, how they interact with light changes. And it's more than just making them small to change what color they are, also changing their shape at the atomic level changes what color they are. There was one person who used this property to make a device that would quickly sequence DNA, that these small particles could be manufactured to bond to various points on the DNA, and so you could do the sequencing very quickly. Very clever idea. This was where I would love to have the video, but we are going to skip over that. Here is a video where it's okay because it has sounds that you won't be able to hear, but it's just goofy music. You don't need to hear the sound anyway. That here you can see that here they've got the nanotube whiskers, and this one has nanotube whiskers on it, and you see that the crud does not stick. Here it's oil. Oil does not stick. And then they have some gloves that they have put the nanotube whiskers onto. And it absolutely does not take on any water, as you will see. Whoa, so cool. Okay. While we're on the subject of nano, this is a scanning tunneling electron microscope, certainly stuff acting at the nano scale. That what you do is between this tip and the sample, you bring the tip close enough that electrons start tunneling that gap, that quantum behavior when there's a barrier here. The electrons cannot move through this space, and yet if you make them close enough, they tunnel, they quantum leap over that space. And so they scan, they move this tip across the sample, and they keep track of the current that's flowing. They keep moving the tip close enough to get a steady current to flow from the tunneling, and they keep moving the tip up and down to maintain that steady current, and they are able to map the surface at the atomic scale. You can actually see the shape of the atoms making up this surface. And I think that this would also be involved in the assembling, putting things together at the atomic scale. And here was an example of what they called a car, a nano car, where they made these things and put them together in this way to make a vehicle that they could drive around on a surface. Okay, now the video.
Imagine a world with buildings that can ride out earthquakes, bacteria that make gasoline, tiny devices that repair individual cells, even DNA, gossamer threads strong enough to hold up a bridge or an elevator to the stars. These visions of the future are based in the discoveries of today, as a new science of materials emerges from the elemental building blocks of the universe, promising a future in which we can create virtually anything we want, atom by atom. Understand. When the switch is off, the computer reads a 0. When the switch is on, the computer reads a 1. String a bunch of switches together, and you can create a code. With just 8 switches, you can represent any symbol on a keyboard. For a page, you need about 25,000 switches. 1.4 million will get you a second of music. Photos need tens of millions. And videos, we're talking about tens of billions. The more switches, the more power. The story of the computer revolution is the story of the shrinking switch. Early computers used mechanical relays and vacuum tubes as switches. Building a machine with just a few thousand took up rooms of space. But the silicon transistor changed all that. Because it's a material, not a machine, it's easy to shrink.
Well, the exciting part about silicon transistors is we're actually using the atomic properties of the silicon. So rather than actually having to craft something, to build the switch, to build the pieces, to build the spring, I actually, by doing some smart engineering, can get the electrons to flow by using the properties of the atom.
Pinning their hopes on a new material that lets electrons flow 1,000 times faster than they can in silicon. It's ultra thin and super strong, and it's called graphene.
And when graphene happened, I just couldn't stop myself from going into it. It was so beautiful, I just couldn't stop. I just immediately jumped onto it.
This is Dr. Pablo Jarillo Herrero, a professor at MIT and graphene guru.
Here I have graphene. Graphene is the thinnest material that exists. This is just 1 atom thick, okay, sheet of graphene, and you can see that it's perfectly visible. So it's part of the magic of graphene that you can just see it, even with your eye.
You heard that right. This gray square of graphene is just a single atom thick.
Add gold to the glass to make it red. It doesn't make any sense. And you know what they told me? We have no clue. But you're the scientist, man. You should be able to explain why gold makes red.
Well, it turns out if you can control the size of a gold particle, if you can shrink it to this nanometer length scale, you have completely different optical properties. Gold's no longer gold when taken to the 13 nanometer size. It's ruby red in color.
When light rays hit a colored material, some colors are absorbed and some are reflected. That's why roses are red and violets are blue. Many metals, like gold and silver, reflect most of the colors in visible light, which is why they can be polished to shine like mirrors. But when a particle of gold is made very small, below 100 nanometers, 100 billionths of a meter, the particle begins to absorb shorter wavelengths of light toward the blue end of the spectrum. The smaller the particle, the more blue is absorbed and the redder it appears. But it gets even stranger, because not only size matters, shape does too. Each of these vials contains water with silver nanoparticles dissolved in it. The only difference between them is the shape of the particles. In this test, silver rods give you yellow, silver triangles green, silver prisms give you blue. If metals behaved like this in our big world, then just changing the size or shape of your car would alter its color. Illness in the body at the same tiny scale.
Okay, so when we inject this, it'll go in the bloodstream and find the cancer, like a rocket guidance system.
Sam Wickline has invented a nano device that's smaller than a virus. Engineered atom by atom, his hunter-killer robots are designed to travel by the billions in the bloodstream. They're pre-programmed by a doctor to seek out specific types of cancer cells and then destroy them, with none of the side effects associated with current drug therapies. It's the ultimate fantastic voyage dream, and it's borrowing a page from these little guys.
Wow.
See here?